Hi friends, this is Rashekar, a GATE faculty for electrical machines. Today in this video, we are going to discuss a problem on MMF balancing equation. In a transformer, problems on MMF balancing, that to unbalanced load conditions. This is very important for competitive exams. Let's see the question. Three single phase transformers of turns ratio 1:2 are connected to form a three-phase star delta transformer as below, like this. This is a star connection and this is delta connection. And then they are asking find the IA value. Find the IA. IA is equals to how much? And here they given a load of resistance are connected to like this, nothing but, see, this is a three-phase transformer, but we are applying only single phase or unbalanced load. This is unbalanced condition. So let's see, this 10 amperes is coming here also 10 amperes, but this 10 ampere divided into two parts. For example, one is taken as I1 and other one is taken as I2. I1 plus I2 is equals to 10 amperes. Remember this. Then next, according to MMF balancing in transformer, MMF balancing equation, see here my IA current enters into the coil at this dot notation, enters into the transformer. If here IA enters into the transformer, here the current in the A phase should be leave from the winding. Then only these two are compensated. Once see here current enters into the coil, but here I1 in the A phase leaves from the coil at the dot notation. Are you okay? And next one, see here this is actually IA, and of course this is IB, of course this is IC. But see here, in this condition at phase B, the current is enters at this dot notation. Current enters into the winding at this dot notation. But see here the IA current comes up to here, and then after this IA divided into two parts. One is taken as minus IB, because this is IB, this is minus IB. There is no current drawn actually. Only the A phase will draws the current from the supply, because we are connecting this is only to the A phase. So only A phase will draws the current. So this IA is divided into two parts. One is minus IB and other one is minus IC, because actually this is IC, but now the current is divided and comes like this. So see here at phase C the current is leaves, but at phase C current is enters here, and at phase B the current is leaves from this dot notation. And see here the current is enters into the dot notation. This is the way of transformer operation actually. So let's draw the MMF balancing equation. Here IA enters into the phase, here I1 leaves from the phase A. So N1 I1 is equals to N2 I2. What is N1? The given turns ratio 1:2. So N1 is the 1. N1 I1. What is I1 here? IA is equals to N1 I1 is equals to N2 I2. What is N2? 2. And what is I2? Here A phase current is I1. We are assuming that I1. So finally here the current is IA is equals to 2I1. Here the current is IA is equals to 2I1. We have to calculate this IA. And next in B here current is leaving and here current is entering. So N1 is the 1 and I1 is the minus IB. N1 I1 is equals to N2 I2. What is I2 here? I2 is I2 only, right? So this is I2. So from this IB is equals to minus 2I2. IB is equals to minus 2I2, or minus IB is equals to 2I2. And next, for C phase again, N1 I1 is equals to N2, and the same I2 current flows through the phase C. So I2. So what is the answer again? IC is equals to minus 2I2 again, minus 2I2. But actually at this point, IA plus IB plus IC should be equals to 0. IA plus IB plus IC should be equals to 0. What is IA? IA is equals to 2I1 plus what is IB? IB is equals to minus 2I2. Minus 2I2 is equals to 0. From this, if you calculated, I1 is equals to 2I1 is equals to 4I2. 2 gets cancelled. So I1 is equals to 2I2. I1 is equals to 2I2. This is the answer. I1 is equals to 2I2. Okay, up to this, I1 is equals to 2I2 and IA is equals to 2I1. Just remember. And now let's see here. I1 plus I2 is equals to 10 amperes. I1 plus I2. But what is I1 here? What is I1 up to we calculated? I1 is equals to 2I2. 2I2 plus I2 is equals to 10 amperes. So I2 is equals to 10 by 3 amperes. I2 is equals to 10 by 3 amperes. We got I2. So this is I2 is equals to 10 by 3. This I2 is equals to 10 by 3. Of course. Can you tell me what is IA? We have to find out IA. But to find out IA, we should know the I1. How we can get the I1? I1 can get by this equation. So I1 is equals to 2I2. 2 times of I2. 2 times of I2. That is equals to 20 by 3 amperes is of I1. We got I1. Then we can calculate IA easily. IA is equals to 2 times of I1, 2 times of 20 by 3. So our IA is equals to 40 by 3 amperes. This is the problem. Actually very simple. Just by MMF balancing equation. By using MMF balancing equation, we can get the answers directly. Like these questions are very important for our GATE exam. Okay? This is very important, I said you. Unbalanced condition, MMF balancing equation. See this question. This is a star-star connection. But in generally, in star-star, many disadvantages are there. There is no path for third harmonics and floating neutral and not a sinusoidal EMF, and we cannot tackle the unbalanced loads. Like many disadvantages are there with star-star connection. To overcome the disadvantages, we are using territory winding. This is the third winding, which is called territory winding. If added this third winding, we can apply the unbalanced load. See, this is the single phase load applied to a 3-phase transformer. We can apply the unbalanced loads by using territory winding. So see here, this is the primary and this is the secondary and this is the territory winding. Here the current I2 they given, territory, the current I2 they given, this is the current I2. I2 is equals to 30 amperes they given. And this is I1. We have to find out this I1. What is the current I1? Of course, for example, in this the current is I3. In this the current is I3. I will tell you what is the notation. Like this they given. they applied a single phase load on this A phase. So let's see, this is a phase and this is a B phase and this is a C phase. A, B, C and A, B, C. They're given like this. Once here, here the load is applied to the A phase. Hence, the transformer draws the current I1 from the A phase only. This I1 is divided into two parts, I said you. So this is the current I1 by 2 and this is the current I1 by 2. These are the two currents. And see here, in phase A, at this dot notation, current enters into the winding. Current enters into the winding here. And here, the current at this condition, at this dot notation, current leaving from the winding. That is the operation of transformer. If in primary current enters, in secondary it should be leave from the winding. Then only it should be balanced. Then only it will balanced. So next one, when comes to here, there is no current circulating in B phase and C phase actually. Because the current is circulating here only. The current is circulating here only. And when comes to here, in the B phase, at this dot notation, the current is leaving from the winding, Nothing but for balancing. For balancing this B phase, there is no current in the secondary. That's why we are choosing the tertiary winding. So now tell me here, to overcome or to balancing this MMF, the current in the tertiary winding at phase B should be leaving or entering into the B phase. Here leaving from the B phase. Here leaving from the B phase. Hence here should be enter. Here should be enter. Here should be enters into the B phase. This is my I3. And see here, also in C phase, the current is leaving. Hence, this I3 should be enters into the C phase. Here current is leaving. Hence, here the current should be enters into the C phase. So this is my I3 and this is my I3. Here also the current is enters into the A phase. This is my I3 and I1 and I2. Now take the MMF balancing equations and find this I1 and they given the turns ratios are 3:2:1. So let's calculate the MMF balancing equation. See here enters into the A phase. Here also enters into the A phase, but here leaving from the A phase. Right? So let's write here N1 I1. What is N1? N1 is the 3. N1 I1 enters. And here tertiary winding also enters plus N3 I3. What is N3? N3 is the 1. What is I3? I3 is I3 only. Is equals to N1 I1 plus N3 I3 is equals to here leaving from the A phase. That is N2 I2. What is N2? N2 is the 2 and I2 is the 30 amperes. So from this 3 I1 plus I3 is equals to 60 amperes is the first equation. And next for B phase. Here leaving from the dot and here entering into the dot and there is no. So one is the leaving, one is the entering. So simply N1 I1 is equals to N3 I3. Right? What is N1 I1? N1 is the 3 and I1 is the I1 by 2 is equals to. What is here? N3 I3. What is N3? N3 is the one because this is tertiary winding. What is I3? I3 is I3 only. So from this I3 is equals to 3 by 2 times of I1. I3 is equals to 3 by 2 times of I1. Right? Next for third one also there is no MMF here. Here leaving and here entering. So N1I1 is equals to N3I3. Again, I3 is equals to 3 by 2 times of I1. These are the MMF balancing equations. MMF balancing equations. Let's take here. Here. 3I1 plus I3 is equals to 60 amperes. But I3 is equals to 3 by 2 times of I1, that is equals to 60 amperes. Our aim is to find the I1. So now tell me, 3 2s are 6, 6 plus 3, 9. 9 I1 by 2 is equals to 60 amperes. So I1 is equals to 60 multiplied by 2 into 60 into 2 by 9. 3 3s are 3 20s are. So our answer is again 40 by 3 amperes. Again 40 by 3 amperes. This is the way of questioning on MMF balancing equation. Very important for our competitive exams. Did you understood? Just what happens are here? Just MMF balancing, which are enters into the winding one side and which are leaving from the winding one side. That is balancing. Then only we can get the answer. Very easy question. Okay? Thank you.